Suppose you're pondering an important decision, such as whether to go on vacation this summer or the next one. It may be that if you go this year, there are two and only two options open to you. You can go to Canada or you can go to Las Vegas. You'll learn from the news that right now there are dangerous wildfires raging in your Canadian destination. And if you go to Vegas, well, every time you've been there, you've come home broke and married to some random stranger. On the other hand, if you wait till next summer, you'll be able to save money and go to Iceland, a place you've always wanted to visit, where you'll be able to get interesting sweaters and go on pleasant hikes. So after thinking things for a little bit, you decide to stay home for this summer and wait for the next. Perhaps this is the way in which you went about thinking about the issue, or at least this is how it could seem to you. You say to yourself, I can go on vacation this summer or the next one. If I go on vacation this summer, I'll go to either Canada or Las Vegas. If I go to Canada, I'll be there from the wildfires. If I do so, I'll get sick. If I go to Las Vegas, I'll come home, if I do, broke and married to a stranger. Therefore, if I go on vacation this summer, I'll get sick, or else I'll come home broke and married to a stranger. If I go on vacation next summer, I'll be able to go to Iceland, where I'll be able to buy interesting sweaters and go on pleasant hikes. So I'd rather go on vacation next summer. Suppose that the self-formalization of your argument contains sentences like these. Regardless of how you actually went about considering the matter, it's unlikely that you went through each of the paths of the corresponding truth tree. This is a very bushy tree, and it only covers parts of the argument. We haven't even considered Iceland yet. And truth tables are even worse. In my formalization of the argument, I could count 12 sentence letters, including Iceland and the sweaters. So the number of rows for the table is 2 to the power of 12. So that makes 4,096 rows. So not only is it unlikely that you'd ever consider thinking about the problem by listing all possible cases, truth table style, but if you did, you'd be saddled with a 20-column, 4,096 monstrosity, which I wouldn't even attempt to diagram here. So if we think of the drawbacks, from the human point of view, of the methods we've studied so far, at least two come to mind. First, they do not seem to correspond to the way we ordinarily reason. In particular, this is a disadvantage if we intend our tools to be used by people. Second, and again from a human perspective, they require a lot of tedious and sometimes quite unmanageable calculation, even for simple situations like the one in our example. In view of this, logicians have devised reasoning methods that are much more direct and economical, that resemble more closely the way we spontaneously reason. For this reason, they are called natural deduction systems. There are several different natural deduction systems for sentential logic. In this lesson, we'll start discussing a very popular one. Okay, here we go. Natural deduction systems are based on the notion of a derivation. This is, I think, an intuitive notion. The idea is that we can show that a conclusion follows from a set of premises by deriving it from the premises. In doing so, we provide a derivation of the conclusion from the premises. So in more formal terms, if D is a sequence of sentences, then D is a derivation just in case each of its members is either a premise or an assumption, and by the way, here we'll only mention premises, and we'll deal with assumptions in a future lesson. So as I was saying, D is a derivation just in case each of its members is either a premise or an assumption, or a sentence that follows from other sentences in the derivation by the application of valid inference rules. These are the only two cases in which a sentence is admitted in a derivation. The first case is when the sentence in question is antecedently given as a premise or assumption. The second case is when it follows from previous sentences in the derivation by the application of inference rules. We'll discuss those rules in a moment. So just for the purposes of this example, let's assume that x1 and x2 are given to us as premises. So in virtue of that, they get to be in the derivation. Also assume that x3 follows from the premise set by the application of a valid inference rule. So it also is admissible in the derivation. Next, x4 follows by another application of valid inference rules from the previous set, and so on. Finally, the last sentence to follow from the previous ones will be our conclusion. The rules of inference are called derivation rules. Derivation rules are truth-preserving. What do we mean by this? Well, a rule is truth-preserving if, whenever you apply it to a true sentence, the result is another true sentence. In other words, a truth-preserving rule will never take you from truth to falsity. So, if the premises are true, then through the application of our truth-preserving rules, we'll guarantee that every sentence in our derivation will also be true, up to and including the conclusion. It is as if the application of our valid rules is a conveyor belt that transmits truth between the various steps in the derivation, up to the conclusion again. Okay, now let's review our system of rules, one by one. As was the case with our rules for truth trees, here we also have two rules for each connective. The first rule we'll consider is very intuitive and is called conditional elimination. It is usually abbreviated as horseshoe E. You would also find it under the names of modus ponens, affirming the antecedent, and detaching the consequent. In essence, the rule says that from a conditional and an occurrence of its antecedent, you can infer the consequent. So if you have a sentence of the form if x then y, and you also have the antecedent x, you detach the consequent y and write it in a separate line. For instance, if x is it rains and y is I'll get my umbrella, then if you have as premises if it rains, then I'll get my umbrella, and it rains, then you can conclude I'll get my umbrella. Makes sense, right? However, you have to be on your guard. Don't confuse conditional elimination with this invalid pattern. If x then y, y then x. A lot of students are seduced by this pattern, but it's a pretty nasty fallacy. If you look at an example, you'll see why. An instance of this pattern would be, if it rains, I get my umbrella. I get my umbrella, therefore it rains. It's quite possible for the premises to be true and the conclusion to be false. So this argument is invalid. Let's see why. Let's grant that whenever it rains, I get my umbrella. So from the fact that it rains, you can immediately infer that I get my umbrella. You can proceed forward in your inference, from the truth of the antecedent to that of the consequent. However, this is compatible with the fact that rain is not the only event that prompts me to get my umbrella. Suppose that I have a very delicate skin, and so whenever it's very sunny, I use my umbrella to cover myself and be protected from UV rays. It might also be that I get out my umbrella when it's windy because I'm obsessed with Mary Poppins. I want to be carried away by the wind. It may be that I'm trained to use umbrellas as deadly weapons, and so whenever I sense danger, I whip out my umbrella. So there are many possible situations that might lead me to get my umbrella. So from the mere fact that I have my umbrella out, you can't infer that it rains because we might equally be in a number of other situations. In other words, you can't reason backwards from the truth of the consequent to the truth of the antecedent. In fact, this is called the fallacy of affirming the consequent. So again, do not confuse this, which is the correct form, with this other case, in which antecedent and consequent are switched in this way. The valid form is called modus ponens or conditional elimination. The invalid form, again, is called the fallacy of affirming the consequent. Okay, enough of that. Now let's proceed to another very intuitive rule called conjunction elimination. This rule is abbreviated as %E. And it says that from a conjunction, you can infer either of its conjuncts. So if you have x and y, you can write x in a subsequent line. Or you can write y, depending on what you need. An example, from grass is green and snow is white, you can infer that grass is green. And you can also infer that snow is white. Disjunction elimination. This rule is abbreviated as VE. And it says that from a disjunction and the negation of one of its disjuncts, you may infer the other disjunct. So if you have x or y, and you have not x, then you can infer y. Likewise, if you have x or y and not y, you can infer x. Suppose that x is you'll win and y is you'll lose. Then from either you'll win or you'll lose and you won't win, you can infer that you'll lose. Similarly, if you have either you'll win or you'll lose and you won't lose, you can derive the conclusion that you'll win. Okay, let's do some exercises. Show that the following argument is valid. Let's start our derivation. On the left, we have our premises. I'm writing our intended conclusion to the right to remind you that it is our goal. So in our next line, we can write not C from line 2 by ampersand elimination. Notice that whenever we make an inference, we have to cite two things: the line or lines where we apply the rule and the specific rule we applied. In the next line, we write A. We get A by disjunction elimination from lines 3 and 4, that is from A or C and not C, respectively. To remind you, this is the inference pattern involved. From X or Y, and from not Y, infer X. Then we can get B. This follows from lines 1 and 2 by horseshoe E. And again, we're following this pattern. So we arrived at the conclusion. And since we derived B from these premises, we have shown that this argument is valid. Okay, let's take a look at more rules. Another intuitive one is conjunction introduction. It is abbreviated as %I. And it says that from any pair of sentences, X and Y, you may infer their conjunction. So if you have X and you have Y, then you can conclude X and Y. Another rule is disjunction introduction, and is abbreviated as VI. It says that from a sentence X, infer the disjunction of X and any sentence Y. So if you have X, then you can infer X or Y. Likewise, if you have Y, then you can infer X or Y. This is because if one of the disjuncts is true, then it doesn't matter the truth value of the other disjunct. The whole disjunct is going to be true. This rule, by the way, is useful for those cases in which you have a sentence that appears in the conclusion but nowhere in the premises. So this is a clue that at some point when you arrive at the conclusion, you're going to use disjunction introduction. Okay, let's do more exercises. Show that this argument is valid. Again, these are our premises. And our conclusion is, as it happens, also B. Out of these two sentences, the only one we are in a position to break up is number 1, which is a conjunction. So we write each of the conjuncts in a different line and justify the step by ampersand elimination from line 1. Then we can get not C. From lines 2 and 3 by V elimination. And now we can get B, again by disjunction elimination, this time from lines 4 and 5. So we reach our conclusion, and we have thereby shown that the argument is valid. Let's do a last one. Consider this argument. What we have to prove is C. The reasonable step here is to apply ampersand elimination in 3. It's the only sentence we can break up. It's the only place where we can start. But then notice that since we have D, we can match the antecedent of the conditional in 2. So we combine 2 and 5 to get not A by conditional elimination. Also, not A is a negation of the left disjunct in line 1. So we apply those two to detach the right disjunct, which we write on line 7. If you had trouble seeing that, remember that the pattern we are applying is from X or Y, and from not X, infer Y. Here X is A and Y is if B then C. Not X then is not A. And the conclusion is if B then C. But we already have B on line 4, so we can apply conditional elimination to get C alone. And we do so and get C from lines 4 and 7 by horseshoe E. Okay, this is all for this lesson. Bye.